Assalamu alaikum. How you doing, guys? Today I'm going to talk about the doubly reinforced beams. I'm going to show you how we develop the equation for the design and analysis of doubly reinforced beams. We're going to solve an example. It's going to be an analysis example. The design example would be in a separate recording following this one. So there are certain instances where I need to keep my B and H constant, whether it's for architectural reasons or I'm insisting in my design to have a hidden beam flush with a column, for instance. Then at that point, I do not want to mess with my B and H. But then if the moment is large, then that cross section might not be able to resist the moment with sufficient steel reinforcement. Actually, now the concrete is going to need help. So we're going to do that by providing some reinforcement on the compression side. So what I'm talking about is actually this right here. So this is my regular cross section. Again, B is the width, D is the distance from the top compression fiber to the centroid of the steel. Now for the compressive steel, which is this one right here, why is it compressive steel? Because it's in the compression zone. And we call this A prime S, or area steel prime. And then the distance from the top compression fiber to the centroid of the steel, we're going to call this distance D prime. Still, I'm going to keep my ultimate crushing strain in concrete. This is going now to be the compressive strain in steel. Still C is the same, A is the same. This is still 0.85 F prime C. The only addition here is the A prime S times Fy. And you notice I've used Fy because in this I'm assuming that both the compression and steel are yielding. So like we did before, we assumed yielding and not yielding. We're going to do the same over here, but we're going to start with the easiest, which is where both of them are yielding. And the way we handle the moment, just to make our life easier, especially from the design aspect, I'm going to assume that my nominal moment is due to two moments. One I'm going to call Mn1, and the other is going to be Mn2. Now Mn1 is going to be exclusively provided by the compressive steel, which is like this. So since this is always going to be less than the tension steel, so I'm going to assume that portion of the tension steel is going to be, again, equal and opposite to my compression steel, and that's going to create a couple. And that couple is going to be equal to A prime S times Fy times the distance or moment arm, which is D minus D prime. So here kind of making a separate moment due to the compressive steel, or let's me call it a compressive steel contribution to my moment. And then the rest obviously will contribute to Mn2, which is simply area of steel minus the compressive steel times Fy times D minus A over 2. And from that, I can find the value for A. Okay? And like single reinforced beams, I also would like to know what will be my row balance and what is going to be my row max for both the double reinforced as well. So for that, I'm going to use the compression is equal to tension again. So my compressive force is simply 0.85 F prime C AB plus A prime S times Fy, and that's going to be equal to my tension force, which is AS times Fy. Now, we're still going to introduce rho as being A prime S divided by BD, but now I'm going to introduce a new rho, which is I'm going to call rho prime, and that's simply going to be A prime S divided by BD. So now replacing the A prime S and AS with rho BD and rho prime BD, then this is going to be 0.85 F prime C beta 1 phi C times B plus rho prime BD Fy, and that's going to be equal to rho BD Fy. Divide that by BD Fy, and the same goes over here. So this is going to be now be rho, and this is going to be rho prime, and then C. Let me do this over here. then C over D is going to be epsilon ultimate over epsilon ultimate plus epsilon y. Okay, so now this is going to be 0.85 beta 1 f prime c over fy epsilon ultimate divided by epsilon ultimate plus sy plus rho prime is equal to rho, and then we know that rho balance actually is this part. So now then rho balance for doubly reinforced, which I'm going to call now rho bar B, is simply the rho balance for a single reinforced beam plus rho prime. Okay, so if I go the same for my rho max, I'm going to reach the same conclusion, in which rho max bar is rho max for the single reinforced plus rho prime, and here I'm just giving you rho max to be as what we found before. If I have a grade 60, then rho max is going to be 0.85 beta 1 f prime c divided by fy times epsilon ultimate over epsilon ultimate plus 0.005. Okay, so again, this is the case where both of them are yielding. Now, if they're not yielding, so the question is, how can I tell if my compression steel is yielding or not yielding? So for me to do that, I'm going to introduce a new reinforcement ratio, and I'm going to call that raw compression yielding. Okay, so if I know what that raw compression yielding is, I will be able to determine if my compressive steel is yielding or not. And to get a limit or a sense of that rho, I'm going to assume that first of all that my rho prime, that my epsilon prime s is the same as epsilon y. So I'm still going to use the same trick. Compression is equal to tension, but now I'm going to find a relation to find this value over here, which is the epsilon prime s. So I'm going to use this triangle, which is epsilon ultimate and c, with the triangle, which is epsilon prime s and c minus d prime. Okay, so these are the two. So this is the second triangle, and this is the first triangle. From that, I'm going to find that c over d prime is equal to epsilon ultimate divided by epsilon ultimate minus epsilon prime s. Again, my limiting case would be when epsilon prime s is equal to epsilon y. From that, I can find a value for c, which is epsilon ultimate divided by epsilon ultimate minus the yield strain d prime. So now with that definition of c, I'm going to go back to, again, compression is equal to tension, 0.85 f prime c ab plus a prime s fy is equal to a s fy. Replace a prime s with rho bd, replace that with rho prime bd, and then replace a with beta 1 c. Now I'm going to divide by bdfy, so this is going to keep rho by itself. Now this is going to be a prime sfy divided by bd fy. Again, since this is the same, so this is going to cancel out with this, so I'm going to be kept with rho prime. Now here's going to be f prime c over fy, beta 1 times c over d. Now replace this c with that, and then my rho cy or my compression yield is going to be 0.85 beta 1 times f prime c over fy, and this is my rho cy that will tell me if my compression steel is going to yield. Okay, so if the tensile reinforcement ratio is less than rho, of course, then rho is less than rho cy, excuse me, then compression steel at failure is below yield, which means my rho need to be more than rho cy for my compression steel to yield, because rho cy was my limiting case. So if rho now is less than rho cy, we call it compression yielding ratio, okay, then it will not yield. So what does that mean? If it's not going to yield, then my f prime s is going to be something less than fy. So for that, now my rho balance is going to be simply rho balance plus rho prime times f prime s over fy. Remember, and when we divided by Fy, it was yielding, so that's the reason why it did not show up here. But since it's not yielding, so F prime S is going to be present, and we can find F prime S from ES times the strain S, and which is this value right here, which is again is less than Y. The same goal for rho max as well. Again, that's the reason why F prime S is showing up here, because it is not yielding. Okay, so the equations on the previous slides, and I mean that for the values of Fs, are only valid with the exact strain values in the tensile steel of epsilon y and epsilon t is equal to that. If the tensile reinforcement ratio again is less than rho balance and less than rho CY, then the tensile steel is yielding and the compression steel is not. Usually for doubly reinforced, we don't have any issue with the yielding of the tensile steel, because it's always going to be less than rho bar balance. Again, the rho balance was the deciding factor if my tension steel is yielding or not. Okay, but again, as I said, usually in doubly reinforced case, it's a really rare case where the tension steel is not yielding. Now, on the other hand, the compressive steel, not so much. It could actually be yielding and not, depending on the moment, depending on the cross-section, depending on the number of steel that is used. So for me to find out if it's yielding or not, first I'll calculate the rho CY. If my rho is less than that, then my compression steel is not yielding. So if I want to find out what my F prime S is, we know that F prime S is epsilon ultimate ES C minus D prime over C. Again, using compression here. Compression is equal to tension. I'm able to find AS Fy, 0.85 F prime C, BC, A prime S, epsilon ultimate ES C minus D prime over C. So from that we notice that C are the only unknowns. Once I'm in, I can find that out, as you know, because a C here becomes more or less of a quadratic equation in C, and we know how to easily solve for that. So if I want to know what my nominal moment is, it is simply going to be 0.85 F prime C, AB, D minus A over 2 plus A prime S, F prime S, again, which we can calculate from this right here once we find out C. So let's start off with an example. In this example, I'm assuming that my Fy is equal to 420, F prime C is 35 megapascals. He's asking me for the design moment capacity of the beam. So again, this is an analysis type of a question. I'm giving you everything. I'm giving you the compressive steel as being 2,525, tensile steel as being 6,532, my H is 700, my B is 300, D prime is 60.5, and then D is equal to 604 millimeters. Okay, again, D is to the centroid of the tensile steel. So first of all, I'm going to calculate rho, and rho is going to be the deciding factor if this is going to be a doubly reinforced or a singly reinforced analysis. Now, rho is equal to the 6,532 divided by BD. It's giving me a value of 0.0266. Now I calculated rho max to be 0.02125, which is less than 0.0266. Thus, it will be analyzed as a doubly reinforced beam. So whenever rho is larger than rho max, it's going to be a doubly reinforced beam. Now, the second step would be I have to calculate the rho bar CY, or the compression yielding strain, to make sure if the compression steel is yielding or not. For that, obviously, I need to calculate rho prime. Rho prime is the 2,525 divided again by BD, and that's equal to 0.054. So now I'm going to rho CY. This is my 0.85. This is now my beta 1. Since F prime is 35, So this is going to be less than 0.85. 35 divided by 4 and 20, d prime over d, epsilon ultimate minus yield, which is, again, we could just use 0.002 without doing this calculation over here. And this is giving me a 0.024. Since rho, which is my 0.0266, is larger than rho cy, then compression bar will yield. Okay. A check on rho max bar, and this is equal to 0.0215 plus 0.0054, it's equal to 0.0267, which is larger than rho. As you can see, it's not larger by that much. Now, if I were doing a design problem from scratch, then I would like to enforce that my rho is less than rho max bar. Now, if you're doing an analysis bit, which means that everything has been done for you, it could be an old design, so you might find out that in certain instances that your rho is actually more than rho max bar, which is kind of okay since it is an analysis problem, so the structure already exists. You have to understand, and there was a shift between the ACI 19 code, which kind of made the rho max a little bit smaller. So previous designs, as far as a year ago maybe, the rho max was a little bit bigger, so which means that the rho max bar was a little bit bigger. So if you find that the only influence that you're going to see in this would be in the value of phi. So going on forward, for design purposes, you always need to ensure that your rho is less than rho max bar. In case of an analysis perspective, if your rho is larger than rho max bar, there's nothing you can do. Continue with the solution and see where will that lead you. Okay, so but for now here in this case we're safe, since again my rho is less than rho max bar. From that, now I'm going to start calculating A, and A is going to be simply AS minus A prime S, 0.85 F prime C times B. This is my 6 phi 32, 2 phi 25. This is 6 phi 32. So from that, I'm able to find my A to be 180.88 millimeters. From that, I'm find my C to be, this one is not 178, by the way. This is 180.88, but this value is actually true. So this is equal to 226.1. Now I'm going to calculate my epsilon t. Again, this is now dt, and that's not d, which is the 604. So now this becomes 0.00544, which ensures me that phi is equal to 0.9. From that now, I'm going to calculate my nominal moment, and that's going to be equal to the area of steel for 2 phi 25 times the yield Fy times d minus d prime plus the 6 phi 32 minus 2 phi 25 Fy d minus a over 2, and I'm getting 1053 nominal moment. My ultimate moment, M ultimate, is going to be phi times this value, which is about 947.86 kilonewton meter. So this section can handle a moment of 947, and that's actually quite an impressive moment. Now we're going to do another example. In this example, I'm using here now 2 phi 22, 5 phi 25, d prime is 59, d is 414, and h is 500, and b is 250. Again, he wants the design moment capacity of the beam. Okay, so we're going to proceed in a similar manner. We're going to find rho to decide whether it's going to be doubly reinforced or singly reinforced. Calculated rho prime, and I calculated rho max, and I found rho max to be a lot less than rho, which means I need to do as a doubly reinforced beam. Then I need to decide whether my compression steel has yielded or not. So for that, I'm going to calculate rho prime, rho bar cy. Here beta 1 is 0.85 because my F prime C is 25. This is my d prime over d, and I found that to be 0.0257, which is less than, or actually raw is less than raw CY, which means that my compression bar will not yield. And since my compression bar will not yield, then I have to find the value of C. So again, here I'm going to use the compression is equal to tension. So ASFY is equal to 0.85 beta 1 F prime C BC plus A prime S epsilon ultimate ES times C minus D prime over C, only known as C. This is going to become a quadratic equation. This is the solution of that. Again, I'm providing this if you want to put that in some Excel spreadsheet or whatnot. If not, just plug these numbers into a calculator, and I think it will be able to solve for C for you directly. So this is the value for G, and this is the value for mu. And from that, I was able to find C equal to 161.07 millimeters. From that, I'm able to find Fs, which is 399.23, which again is less than 420, enforcing the fact that my steel has not yielded. From that, I'm able to find A. And I would just want to double check with raw max bar. So when I calculate raw max bar, you've noticed that this value is less than raw, because raw is 0.0237. I mean, it's not less by that much, 6 in the 10,000s, if you will. But still, if that was a design problem, if I was designing that for scratch, I probably would go back and do some changes. But since this is an analysis problem, and this problem is given to me, I will still finish the analysis till the end. The only influence here that might happen is in the value of phi, because remember, one of the stringent things about the code this time around is I want your phi to be 0.9. I do not want it to be less than 0.9. I want my cross section to be totally tension controlled, not compression controlled. Okay. By the way, this example, I used the same example before, which I used to design back in 2018 on the old Romax, and it was safe. I mean, it was less than Romax. But again, with this new change, it is not. So continuing on, I will calculate now the net tensile strain in the tension. And again, this is now dt. And as you can see, it's very close to my 0.00518, and my phi is still 0.9. So although it was less than Romax bar, but still my phi is 0.9, so I'm still good. Then my nominal moment is now going to be, again, this is my, I guess, 2522, if I remember correctly. This is my Fs, which again is less than Fy, D minus D prime. I think these were the 525 minus the 2 phi Fs over Fy, and this is Fy, D minus A over 2, and this is giving me a total moment of 360 kilonewton meter. Now M ultimate is just phi Mn, and that's 0.9 times Mn, so this cross section can hold only up to 323.63 kilonewton meter. The takeaway from this, again, if your compression steel is not yielding, then the extra step that you have to do is to find that Fs. I mean, that's the only thing that's, I guess, an added step in this example. Also, we found out that my raw was larger than raw max. I mean, it was a little bit, but you might find cases where it might be a little bit more than that. But again, the old designs were set up this way. So the only influence that I can see would be in the value of phi. So instead of that being 0.9, it might be 0.85, 0.86, which means you will have a less ultimate value to post on your design. So this will end this portion for doubly reinforced beams. The next recording will be a design example. So you guys have a good day and stay safe out there.